That leads us to a very important molecule. I'm just going to pull this picture up here, called ATP, adenosine triphosphate. And ATP ends up being the molecule that is used in this top exergonic reaction. So I just drew these two squares together. The ATP ends up being the molecule that we oftentimes use as our source of energy. And so the way it works here, ATP is made of an adenine group. That's this up here. It's a nitrogen base. An adenine group, a ribose, which is a pentose sugar. We can call the two of these together adenosine. Okay, and then it's going to have three phosphates, and I'm noticing now that there's not a P in the middle of each of these, so there should be a P there, and a P there. So the triphosphate means three phosphates. Phosphates end up being negatively charged. You can see all of these have a negative here, a negative, a negative, a negative. And so if I'm going to have a bond that holds all these negatives together, it actually is going to require a handful of energy there. And so there ends up being energy stored in trying to hold these phosphates together. And so specifically this bond right here between the second and the third phosphate, this bond ends up being broken oftentimes to release energy in a cell. Okay, and so that's ATP. On the next slide, we're going to kind of show how that energy release works here. So here we have a quick view of that hydrolysis of the ATP. And we're starting with an ATP molecule up here on the top, ATP molecule, which again would have energy stored in that bond right there. And if we do hydrolysis, so adding water, breaking that bond, we end up with that one phosphate being left by itself over here, and then this is now called a DP, D for diphosphate. Anyway, and it releases energy, so this is the payoff over here, energy. Specifically, how much energy per mole of ATP? It's going to be 7.3 kilojoules, or kilocalories, excuse me, kilocalories is the unit they're using, per mole of energy. What that can be used for is we can take the energy that's released there, and that's enough energy to feed into a reaction that requires 7.3 kilocalories per mole or less. Okay, so if it needs more than that, then we'd have to use 2 ATP or something like that. But we have enough energy to run a reaction that would require less than 7.3 kilocalories.